I would like now to switch again in English and ask for our last speaker on this session, Mr. Stelios Lampadakis, to come on stage. Mr. Stelios Lampadakis is a mechanical engineer and HVAC consultant. He graduated from the National Technical Institute of Greece in 2000 with bachelor's degree in mechanical engineering. Ever since, he worked as a sales engineer, project manager, and design engineer in commercial and design application companies. Today, he's going to present us a very interesting topic, which is the indoor air quality, the phenomenon of sick building syndrome, health and productivity impacts on HVAC solutions.
Thank you, Stelios. Thank you, Stelios. Good morning to all. And first of all, I would like to say thank to the Hellenic chapter that's given me the opportunity to be today here with you and discuss this very interesting subject of the indoor air quality and the sick building syndrome. Today we will try, first of all, to define what is the sick building syndrome. We will try to see what exactly, which are exactly the health and productivity impacts of the syndrome, the relation between the SBS and the comfort conditions of a building, and of course, the solutions that HVAC engineers should suggest in order to eliminate these impacts. By the beginning of time, the involvement of human society is working hand by hand with urbanization. And from antiquity until nowadays, the size of the cities constitutes an indicator of the prosperity and the economical growth of the cities. Nowadays, the globalization leads to the extension of the urban landscape, and according to the United Nations, the review of 2020 of the United Nations, the urban population was 47% in 2000, and the prediction is to rise up to 60% until 2030. Unfortunately, as we all know, every good has its price. So, in our case, in urbanization brought diseases, let's say the plague of Athens, the great plague of Antonin, plague of Justinian, the great plague in London and in Marseille, with many casualties and victims. Despite the fact that each plague had a different cause, in all of them, we have some common, let's say, reasons that triggered the plague. And this is the high density of the population and the lack of fresh water or sewage network, and of course, underestimating the hygiene rules. So, what we need to feel comfort, and what is that urbanization doesn't give to us as people. Actually, we are children of this planet, and we feel happy when we have sunny, bright light, and warm weather, clean air, and calm and quiet environment. Actually, these four statements are the comfort conditions, but we will see it later. Now, in the modern cities, we have the opposite of of what we need in order to feel comfort. Because there are loud and crowded roads and big streets, we have polluted air, and we live mostly in buildings with artificial climate, and all these lead us to, let's say, being away from the nature. A building is considered sick when the inhabitants don't feel comfort in it. And this is the first thing that we have to see, that the sick building syndrome affects the inhabitants of the building. For me, the SBS is not a syndrome of the building itself. It's a syndrome of the inhabitants of the building. And the only reason for the sick building syndrome is the poor comfort conditions in the building. According to the World Health Organization, I will take now a big breath. Sick building syndrome describes a medical condition where people in a building suffer from symptoms of illness or feel unwell for no apparent reason. And I think that the key factor is the for no apparent reason. We don't know the reason. So we are going to the doctor, we have sickness, we don't feel good, we feel well, let's say, but nobody can find what is exactly the problem. The problem is not an apparent reason. The problem is the building. We spend more than 90% of our time in buildings with artificial climate. And according to ASHRAE fundamentals, this might be more than 90%, 96%, if we calculate also the time that we spend in our vehicles. And affects the sick building syndrome, affects at least once 60% of occupants of a sick building. Now, what exactly can we say that are the impacts of the sick building syndrome? First of all, we have health impacts, and secondly, productivity impacts. The health impacts might be short-term. Let's say that we have two categories of short-term health issues and long-term health issues. The short-term impacts might be nausea, headaches, respiratory issues, fatigue, irritation, especially in eyes, throat, or nose, and stress. And the long-term impacts might be cancer, respiratory diseases, and heart disease. About the productivity impacts. According to a British study, the review says that we have loss of productivity between 3% for staff that takes sick leave and 33% for staff who are sometimes less productive. This is a very big percentage of loss of productivity. And in USA it's estimated as a loss of $5 billion annually, and this is 0.5 to 1% of GDP. I tried to find statistics for Greece, but it was very difficult. But as you can see, it's a very important matter. It's a very important issue. Not only if we see it about our health, but also about from the economical aspect. Now, I know that almost everybody here know about the comfort factors, and it's familiar with them, but let's have a small quick remind. We have 4 factors. It's the thermal comfort, the visual comfort, the acoustic comfort, and let's say air quality comfort. It's not exactly, I'm not use this term, but okay. Okay, it is very difficult to define what comfort is exactly. So because comfortness is something that we evaluate with different way, each of us. So this is an example. Okay, let's say that we have a climax from 0 to 3, and by saying 0, we don't feel comfort, we feel totally uncomfort in the place, and 3, we feel perfectly comfortable. Okay, it's just an example. And if we evaluate how do we feel in a room, let's say that we feel perfect thermal comfort, it's more than good, let's say visual comfort, it's poor air quality and perfect acoustic comfort, then the area of this rectangle, it might be an indicator of how comfort we feel in the building. In our presentation, we will talk only about thermal and comfort and about indoor air quality, not air quality comfort. This is a balance. Professor Pavel Olaf Fanger was a pioneer in terms of evaluating the thermal comfort. His research in late 60s remains until nowadays the fundamental base of comfort evaluation. He created the orphan decibel units to measure the indoor air quality. He connected the indoor air quality with asthma development in children, and he inserted the statistic model of PMV, that means predicted mean value, in thermal comfort. That remains the most accurate tool for thermal comfort calculation until nowadays. Of course, there is a standard from ASHRAE about thermal comfort. It's the standard 55 that it has been revised in 2023. It's quite new. According to this standard, thermal comfort is that condition in mind that expresses satisfaction with the thermal environment. That means that the human body does not start the thermoregulating procedure. So we don't need energy to change our body temperature. And according, again, the standard, we have two big categories for the comfort factors, the personal factors and the environmental factors. The personal factors, we can say that we have only two, clothing and activity. So when we have a room, the type of clothing of the inhabitants of the building is one factor that the engineer cannot do anything about this, only predict what the type of clothing the inhabitant will wear. And the activity, again, it's a personal factor. Again, the engineer cannot do anything about this, only take it in his mind when he's making the calculations for the building. The environmental factors, it's air temperature, radiant temperature, airspeed, and humidity. This is the factors that we actually need to change in order to make the occupants of the building feel comfortable. So about clothing, the unit is CLO, clo, from clothing, and as you can see from the definition of the unit, it actually represents the thermal resistance that the clothing provides to our body. And in the standard, you can find a lot of tables with several values of the CLO. You can find also some combinations of clothing types, but you can find more analytical tables if you want to play and see what happens and if you are going to have the same results as the basic table with the combination of clothing. And if we want to see how the comfort feeling changes with different types of clothing, we have here an example. If we have someone that is wearing clothing that provides 1 CLO of thermal resistance, then the zone will be from, the comfort zone will be from 19 to, let's say, around 25, 24.8 degrees of Celsius. And if we change the clothing to 0.65, so it's a lighter clothing, we have a zone of comfortness from 22 to 26.5. This is something that everybody knows it, but what the standard gives us is a calculation tool. It's a way to predict how the persons will feel. About the activity, the unit is MET from metabolic. It's actually the energy that, the thermal energy that the human body produces per square meter of human body that is exposed to the environment. And also we have a lot of tables with almost every human activity in the standard. And we can find, for example, the MET for someone who is sleeping. We can find the MET for someone who is walking, and etc. Now, about the environmental factors, we have the air temperature, the humidity, the airspeed velocity, and the radiant temperature. And as we know, air temperature and humidity are always working hand by hand. So if we see here the psychrometric chart, we have in the area of 58 kilojoules per kilogram of dry air. And we will examine what happens in 60% relative humidity and 40% relative humidity. We can see that the dry bulb temperature, so let's say the sensitive temperature, will be 26.5 and 30 degrees for these different situations. About the airspeed, it's much more complicated because it depends where do we feel the airspeed and in which period, and sometimes we need the airspeed, sometimes we don't. For example, in the winter time and when the system is working in heating mode, the ambient temperature, you see ambient temperature is defined as 10 centimeters from the ground. If it is too high, we will feel that we are colding. We will feel uncomfortness, even if the room temperature or our thermostat is saying 20 degrees. 20 degrees it looks fine, yes, but if the temperature is, if the airspeed movement is more than 0.2 meters per second, this will produce discomfortness to our body. This is an example. From the other side, in the summer period, we all know the ceiling fans, and the ceiling fan is something very simple that doesn't actually change the temperature of the room. It changes only the evaporation of the film of sweat from our body. And as we know, evaporation absorbs energy from our body, and we feel cooler when the speed is higher in the summer period. Of course, there are limits in everything, okay? So we cannot bring a typhoon in a room in order to feel comfort. In this example, we have airspeed movement in the room, 0.1 meters per second. In this case, the desired temperature in order to feel comfort is from 22 to 26 degrees. And if we change the speed to 0.5 meters per second, then we have from 25 to 30 degrees. Last but not least is the radiant temperature. It's very important for our feeling of comfortness. The radiant temperature is also a little bit complicated because, first of all, we have the radiant temperature that it is actually because we are exposed directly to the sunlight. This is something different from the radiant temperature of the surfaces of a building because we have a radiant heating system or a radiant cooling system. Of course, in the ASHRAE standard 55, you can find a lot of tables. Here is a table that calculates the exposure of the human body to the direct sunlight and sunbeams, and also the transmission of energy from the sun to our body. So it changes for us the temperature, the surface temperature of our body. And we have the thermal sensation scale of ASHRAE. This is a 7-step scale. It's from -3 to +3, from cold, cool, slightly cool, neutral, slightly warm, warm and hot. Of course, the neutral, the value of 0 is the desired step. And from here, we have the predicted mean vote. It's something that we said before about the PMV value. The predicted mean vote is a prediction, according to our calculations, of where it's going to be, let's say, the evaluation of the comfortness in the building that we calculate, that we study. Of course, this is the equation that gives us the PMV. And we have only two factors in this formula. The M is the level of metabolic activity, so we can take it directly from the tables that we saw before. And the L is, again, I will need also a big breath, it's the thermal load on the body defined as the difference between internal heat production and heat loss to the actual environment for a person hypothetically kept at comfort values. What is this exactly? This is the thermal comfort equation of Professor Funke. So nowadays we have a lot of new variations of the thermal comfort equation. If you try to find it, you will see that there are more than 10 different variations of this formula, but they are giving almost the same results. So the PMV value, no matter how you calculate it, will be the same. And also, We have the predicted percentage of dissatisfied. This is the percentage of people that will not feel comfort in the building. And the equation for the PPD is this one that, as you can see, the only connection with the PPD is the PMV, it's nothing other. So here is a graph. We will see that the desired point of 0 for the PMV give us something like 5%. That means that we cannot make everyone happy in a building, okay? Always there will be a percentage of people that feel dissatisfied. For us, the ideal is to be around 0 PMV and around 5 PPD. About the quality, we all know that there are a lot of contaminants in the air, like dust. And the dust, we mean asbestos fiber, plaster, soil, dead human cells, hair, and we have gaseous contaminants like carbon monoxide, oxides of nitrogen, oxides of sulfur, carbon dioxide, formaldehyde. We have microbia, bacteria, staphylococcus, coronavirus, streptococcus, legionella, fungus, and of course we have the VOCs. The obvious solution for providing good air quality to a room is a lot of fresh air. Okay, but this is difficult to be achieved due to extra high energy costs for cooling or heating the fresh air that we are keep on putting in the building, high construction costs for air ducts sometimes, non-stop air vents consuming continuous electric energy. Sometimes the fresh air, it's not very fresh, especially in big cities. And so the modern HVAC design focuses in heat recovery systems, recirculation of the air, filtration, purification, and continuous measurement of the air quality. The air purity needs a variation of indicators in order to be measured. So we have measurement of CO2 concentration that mainly indicates human activity and presence in a building. VOCs, volatile organic compounds, outcome of chemical products mainly, such as cleansing products, and microparticles like dust, bacteria, etc. Of course, I know that you have already imagined it, there is also another standard from ASHRAE about this, is the standard 62.1 and 62.2, revised in 2022. And in this standard, it's a very interesting standard, you can find everything that you need about the indoor air quality. For example, you can find these tables. I know that I don't have, but I want to say this example. In this room, we are around 140 persons now, and there is always a matter for the study for us. Shall we calculate the fresh volume of the air by the cubic feet, the cubic meters of the room, and say, let's say I'll give 3 changes per hour for this room, or by persons, or by the activity of the persons, and what other things are in here, like let's say we have an oven, and you don't have nothing to consider more than just open the standard, and you will see a solution for every problem like this. You will see that there are for a cafeteria, for a kitchen, for break rooms, for everything, for almost for every activity, and for every type of room, you will find the advice that you need there in order to choose the perfect solutions for your calculations. And by saying perfect solutions, you have to combine two things in our mind. First of all, the conditions of comfortness for the people, and secondly, the energy efficiency of the system. Now, the common problems that we have in our calculations, we can see is miscalculation of heating and cooling loads, wrong design of the HVAC systems, and by saying wrong design sometimes is something very, very simple, like the wrong position of sensor or thermostat, or the wrong positions for air grills that produces bad, let's say, make us feel uncomfortable. For example, an air grill that blows cold air behind your neck in your office, even if the temperature in the office is right, you will not feel comfortable there. Inadequate maintenance, especially in filtration systems, lack of automation and control, and wrong building materials or wrong use of the building materials. And of course, we have the underestimation of importance of the HVAC systems in comparison with the interior design, especially when it comes to the cost. Eventually, maybe the owner of the building will prefer to spend more money for painting inside the walls, but he will not give you more money to have a better system of heating, cooling, or ventilating the room. Summarizing, the sick building syndrome affects all urban citizens. The phenomenon impacts health and productivity. The only reason of the syndrome is the loss of comfort in the building. And we, the HVAC engineers, must design new buildings and renovation according to standards that prevent the phenomenon. And something very important, a sick building can be healed. That's all. I don't know if you want, if you have any questions.